welcome to weeks 3 and 4. We're going to be talking a little bit about vector functions, just chapter 13 in your book, Stewart text. Be sure to look through all your textbook pages and read for more concepts, objectives, and examples in the chapter, as this will not be comprehensive, but just point out a few important points. So let's get started. So what are vector valued functions? Vector valued functions, or VVFs, are functions of a real variable t whose outputs are vectors. So they have a form r of t is equal to f of t, comma, g of t, comma, h of t. And what they're used for is to kind of describe space curves. You can draw the VVFs using 3D calculator online or programming Calc.com if you're into Python. You could also sketch the vectors by hand, as we'll see in the next example. So we have to sketch 2 cosine ti plus 2 sine tj plus 1 k. So in this example, I'll just go through it. I already wrote out the solution here, but you could put this in component form. We see z is equal to 1 because there's a 1 in front of the k. And we see that the first component and second component are in the form x equals r cos t, y equals r sine t, and that is a circle of radius 2, and where z equals 1. So we could draw a circle centered at 0 of radius 2 at z equals 1, and then we need to put a little orientation on it. And how we do that is we take a couple of points where t is increasing, so 0 and pi half, and we see we get these points here. So we get a counterclockwise motion on this space curve. So it's just a circle that's rotating counterclockwise here. Now, derivatives and integrals of VVFs. The derivative and integral of VVFs are just like what you think of in standard single variable calculus, so except it's just component wise. Okay, so that's the main difference between dealing with single var and dealing with multivariate in this case. You also want to be able to find this standard unit tangent vector of VVF at a point. And this can help describe the movement of a vector as t increases. So you can think of like linear speed as a tangential speed on a rotating object. So let's look at an example. So with this example, we want to find the domain, we want to find the limit of r of t as t approaches 0, then finally find the derivative. So to find the domain, we just consider all 3 parts. So in the first part, we know that 2 minus t has to be greater than or equal to 0. In the second component, you see that t cannot be 0. And in the last component, t plus 1 has to be greater than 0. So that being said, we get the domain D is -1, 0, union 0 to 2 bracket. Okay, so that's going to be the domain of our VVF. Next up, you find the limit of r of t as t approaches 0. And that you can just plug in 0 for the first component and for the last component, because both of those components will be continuous at 0, t equals 0. However, the middle component is not, so we have to still evaluate that limit, and that's an indeterminate form of 0 divided by 0, so we could just use the L'Hopital's rule from single variable calculus to evaluate that limit. We see that limit is equal to 1. Finally, we have to find r prime of t. So here you just take the derivative component-wise. On the first one, we use the chain rule. On the second component, we use the quotient rule. And lastly, the third component, we just use the property that you take the derivative of ln of t plus 1. It's 1 divided by t plus 1. So this is just using the common rules you know from single variable calculus. Not much that's really new here to see in terms of computations that that you know from Calc 1, Calc 2. Alright, so we need to find a vector function that represents the curve of the intersection of these two surfaces. So on the one hand, we have a cylinder, x squared plus y squared equals 4, and we have a surface. So what we want to do is look at the solution. Oops. Is we want to parameterize this to cos of t, because we realize that this is just basically a circle of radius 2, r is 2, y is equal to 2 sine t, and then what is z? Z is x times y, so what is that? That's 4 sine t cos t. So we just put that vector function, maybe in component form, 2 cos t, 2 sine t, and that's 4 sine t cos t. So that's the vector representation. All right. So that completes this problem. Let's talk a little bit about arc length and curvature. So a few objectives that we want to be able to do here. We have to be able to compute an arc length of a curve. So this is similar to single variable parametric case of computing arc length. And 3 variable is very similar to computing arc length in 2 variable or single variable calculus. So it's very similar to what we've done prior. Know how to compute curvature and the definition of smoothness. So parameterization r of t is called smooth on the interval I if r prime is continuous and r prime is not 0. So as it turns out, smoothness is a very important idea because if you don't have a parameterization that is smooth, then many of the things that will come later on you'll not be able to compute. So this smoothness condition is essential, really, for our computations, for many of our computations moving forward. We have to know how to compute the unit tangent vector, t of t, and when to use it. We have to know how to use 3 equations of the curvature, and we have to know how to compute and use the principal unit normal vector, or just called sometimes a unit normal vector, nth of t, among other things, right? So there are other stuff in there as well that you can see. So say if we want to find the length of this curve, okay? So this is nice and this vector value function is a function of t, right? So we want to be able to find length of the curve using this formula. L is equal to, and here we're going 0 to 1, so 0 to 1 square root, and this is the formula for computing the, these are primes here, computing the arc length. And here f of t is here, g of t, h of t, so you have to take the derivative of each one, then square them, then take the square root of the whole thing, evaluated 0 to 1. And now sometimes we'll be using computer softwares to kind of do these calculations for us because you know, it's much more efficient, but should at least minimum show the setup of how we do this computation. So so let's see, first one we're going to use the power rule. So let's just do that. So we get 3t to the 1/2 squared plus negative 2 sine 2t squared plus 2 cosine 2t squared dt. And maybe we can simplify this a little bit. Let's take a look. 0 to 1. So we get 9 here and 9t. This becomes plus 4 sine squared 2t plus 4 cosine squared 2t dt. If I factor out the 4 there, right, I'm going to have 4 times sine squared plus cosine squared. That's equal to 1. Sine squared plus cosine squared is equal to 1. So I'm just going to get 4 out of that. So that definitely simplifies a little bit using a trig identity. 9t plus 4 dt. Alright, so that's certainly a lot easier to deal with because you can make a u substitution. For example, so du over 9 is dt. And let's see, we get L is equal to, when t is 0, we have u is 4. When t is 1, we get u is 13. 1/9 comes out on the outside. Square root of u du. And this is just a power rule of integration that we need to do. So we can just try to compute this real quick. So we get u to the 3/2. So 2/3 u to the 3/2 evaluated from 4 to 13. And that's just a matter of, let's just come upstairs, running out of space here. That's just a matter of computing this. So L is going to be 2 over 27 bracket 13 to the 3/2 minus 4 to the 3/2, and whatever this comes out to be, it is. Okay, so you can use a calculator at this point to estimate this value if you see fit. That's fine. So yeah, this is not really much different than a 2D case where you parameterized, you know, just let's say f and g, so you have a parameterization for x and y. It's pretty much just an extension of that. So there's not a whole lot that that is different here. All right, so that's how you compute the length of a curve. Let's look at how do you find the unit tangent vector, how do you find a unit normal vector, unit binormal vector, and then finally the curvature given a VVF. All right, so now this becomes a little bit, this may seem like a very short question, but actually it's not that short of a question, and computationally could get rather involved, depending upon what you're given. Again, right? If you're given something very simple, then the computation will be relatively straightforward. But if you're given something a little bit more complicated, then of course computation is going to be a little bit more cumbersome, and we need to pay particular attention to it. So let's try to find out the first one. So let's try to find A first. I'm sure one problem might take up a whole slide, so let's go. So let's find r prime of t first. So we'll just use a chain rule. So this is 3 sine square t cos t. 3 cos square t times negative sine t. And finally 2 sine t cos t. This is again just using chain rule. Sorry, I got a little squished there, but that's our prime of t. Now what we need to do is we need to compute t of t. T of t is the unit tangent vector, which is r prime of t defined as r prime of t divided by the length of r prime of t. So we got r prime of t, we found that, but we don't know what the length of that vector is, so we need to compute that. There's going to be hopefully some simplification and some division going on, where we can simplify this in a kind of a nice way. So let's go. Let's compute the length here. So the length is just the square of each one of these. So if I square the first one, I get 9 sine to the 4th t cos square t plus 9 cos to the 4th t sine square t plus 4 sine square t cos square t. And then we look to see if we can have any identities that we could use or anything that's in common here. So I see sine square cos square is in common. So let's bring out sine square cos square. T. And what are we left with? 9 sine square t plus 9 cos square t plus 4. And there we see 9 square, 9 sine squared t plus 9 cosine squared, that's just 9. 9 plus 4 is 13. So this actually works out to be 13. So, and when I take the square root of these two, the squares drop out. You have to be a little bit careful with that because sine and cosine, that multiplication, they're, if you drop this out immediately, um, that could become negative depending upon what t is. So we'll look at that in just a second. So we got what? Square root of 13 sine t cos t. And so long as t is in the first quadrant, right? T is in the first quadrant, t is positive, so we don't need to do anything too funky over here if we just have t in this interval, right? So this will work. All right, so now I have to divide r prime of t by the length of r prime of t, and then we'll find t of t. So maybe there's a little room here. I'm going to try to fit it up here. T of t is equal to this guy divided by this guy. You know what? I'm going to go to a new slide. So, new slide. T of t. Don't mind me. I'm just going to bounce between two slides. 3 sine squared cos t. Cos squared sine negative sine t, so negative 3 cos squared t sine t, and 2 sine t cos t. That's all divided by root 13 sine t cos t. We just divide each component by that, right? So, and we want to try to make it as simple as we can. So let's go. So 3 over root 13 sine t, negative 3 over root 13 cos t, and we just get 2 over root 13 for the final component. You can bring out that root 13 in the front, so 1 over root 13 times 3 sine t negative 3 cos t 2. So that's a unit tangent vector. So if we need a unit tangent vector when t is 1, all you do is you put in t is 1 and then you get the unit tangent vector. So this is kind of useful because it's good for any value t that you want, so you can find any unit vector, any tangent unit vector that you want throughout this whole space curve. So that's kind of nice. So that's just A. So for B, the unit normal vector, it depends on the unit tangent vector, all right? So basically what the unit normal vector is, and I'll go to the next slide after this, is n of t is equal to t prime of t divided by the length of t prime of t. So that means that I have to take the derivative of t,